This episode of Physical Attraction is sponsored by Podcorn. Some of you out there may be fellow podcasters, e.g. if you're in our Science Podcasts Facebook group. If so, you'll know the extraordinary amount of work that has to go into researching, writing, recording and editing your own show. If you're a small indie show like this one, getting sponsorships to make what you do even remotely sustainable can be tough. Podcorn are aiming to change that. It's a place where podcasters can go to pitch ad space on their shows to people who might want to work with them. One advantage to this is you do get to pick who you work with. I know other shows use dynamic insertion, which is done by their podcasting company, and therefore they end up filled with extremely ironic ads for people they've just criticised. This way I can filter out neoclassical economists, fossil fuel companies, any governments that I've criticised, and flat earthers, so it's all good. If you're a podcaster and you want to find out more, check out the Podcorn link in our show notes, and thanks for listening to this and helping me buy more caffeine. Hello and welcome to Physical Attraction. This episode is going to be about machine learning and climate change, and it's in part based on an article I wrote for Singularity Hub, expanded with some additional content. And it's in part based on my experiences at the Machine Learning and AI workshop at the International Conference on Machine Learning back in 2019. Climate change is one of the most pressing issues of our time. Despite increasing global consensus about the urgency of reducing emissions since the 1980s, they've continued to rise relentlessly in the decades since. We look to technology to deliver us from climate change, preferably without sacrificing too much in the way of economic growth. Our optimistic, some would say techno-utopian visions of the future involve vast arrays of solar panels, machines that suck carbon dioxide out of the atmosphere, and replacing fossil fuels for transport and heating with electricity generated by renewables instead. And this is really nothing less than rebuilding our civilization on stable, sustainable foundations. Meanwhile, though, society is increasingly being shaped by machine learning algorithms, automating occupations, performing tasks from diagnosing illnesses to serving up adverts, and nudging people into different behaviours. So how can AI and machine learning be used for good to help in the fight against climate change? In many ways is the answer. Just as tackling climate change involves practically every sector, agriculture, transport, architecture, energy, industry, logistics, to name but a few, so machine learning solutions can find their niche to help solve some of the thousands of problems that arise when you try and decarbonise the economy in every single sector in this way. This can range from improving our understanding of the problem by making better climate models, helping businesses and industries reduce their emissions, aiding in the design of new technologies, or helping society adapt to the changes that are already on the way. Now, recently there was a team of researchers from multiple universities, including figures like Coursera founder Andrew Ng, chief scientist of Google John Platt, and Turing Prize winner Yoshua Bengio. They've teamed together with a bunch of other researchers and published a 100-page research paper outlining some of the areas where machine learning is best placed to make a difference. So one example would be balancing the grid. A classic example is in the field of renewable energy. Solar and wind are now in most regions the cheapest electricity generation to build, even without a price on carbon. The main barrier that's going to prevent them from immediately just taking over 100% of generation is intermittency. How to integrate these power sources, which vary with the weather and seasonally, onto a grid that's driven by human demands. And doing this efficiently allows us to minimise the amount of fossil fuels that we burn, but it requires skill, both in forecasting the supply and demand of renewable electricity. Now, machine learning algorithms basically process huge amounts of data, and they can do it from real-time weather conditions to information about pollution to video streams from areas near solar panels, and they can rapidly convert these into predictions for the amount of power that will be generated. Beyond just forecast, though, machine learning algorithms can be in charge of scheduling and dispatch, determining which power plant should operate at any given time and which can be switched off. Now, of course, they can do this to maximise the profit of the company that's running the various power plants, but they could also minimise the CO2 emissions that are going to be generated by running the grid in a particular configuration at a given time, depending on this changing supply and demand. In the future, Internet of Things technologies may well provide more flexibility for demand-side management. In other words, the most power-intensive processes can take place when the supply peaks, avoiding wasted energy and overproduction. This could happen in industry, where you try and time the cycles of your industrial processes so that, for example, you're using heat when there's a lot of excess generation on the grid. Or it could happen within your own home, where you do things like dishwashing or washing machines that aren't time sensitive, can take place when there's supply peaks rather than when there's demand peaks, which is going to reduce the amount of stable baseload power that you need to run your grid. And in turn, that will enable intermittent renewables to be integrated onto the grid with less storage and less use of resource. Now, the electrification of transportation is also going to add a huge amount of local storage options to a more complex grid. You can have these large batteries of electric cars, which could end up being used to power your home, and the first models that can actually do this are forthcoming. But then you run into the issues of, okay, how do you do this in a green and sustainable way? When's the best time to draw power from the battery and when isn't? And all of that sort of thing is something that a machine learning algorithm could potentially be used to process the data associated with that and make the decisions associated with that. Now, controlling such a network of supply, storage and demand in the presence of uncertainty and streams of data from millions of different sources is a job that machine learning might excel at. Algorithms such as those which serve up adverts, they already use this mathematical infrastructure like bandit theory to decide which action they can take to maximise a given reward. So you can imagine, with some obviously quite substantial adaptations, but the basic mathematical theory is there, you can imagine a world where machine learning algorithms figure out which piece of storage to switch on now, which piece of grid to switch on now, which piece to switch off, in order to minimise the overall CO2 emissions of the grid. And hopefully that reward again will be maximising the green amounts of electricity that are being used at the moment and minimising emissions rather than just maximising profit for the electricity company. Now, there are further areas where machine learning techniques have already been developed for other industries which could potentially be adapted for the fight against climate change. For example, hedge funds, financial services companies and so on, they employ people to write machine learning algorithms that will use natural language processing. So these are a whole class of algorithms that basically just try and interpret writing, usually. They can read and analyse sentiment by churning through vast volumes of text to help determine which companies are worth investing in by going through the financial news. In fact, an awful lot of financial news is even generated by such algorithms, where they basically just stitch together key aspects of the profit or loss of the companies, the share price fluctuations of the companies, the debt to equity ratios and so on. And if you've ever read any financial news about specifically quite small companies where no one's writing proper articles about them, you'll see that most of it is generated automatically by these machines in a way that looks like a coherent article. But you can imagine that although these things are currently being deployed to scroll through all of this text and try and determine whether a company is profitable and worth investing in, you could deploy similar algorithms to trawl through the huge amounts of documents published by companies, news articles about them and so forth, to give them climate scores which will determine which of them are taking the most proactive measures on the environment and to seek evidence that they're complying with the relevant laws. And then they could flag up potential issues earlier on without having to have a human basically trawl through all of these different articles by themselves. And already we're seeing, for example, the role in the law of the paralegal, which is going through case law, case history, and trying to determine what precedents exist. This is being automated and being replaced. And this could have aspects and where it could be used for the increasing field of climate-related litigation. There's something I've wanted to do an episode on for a while, but this is the idea of people being sued for climate damages and people holding companies responsible and companies to account for their carbon emissions. And obviously there's a lot of precedent for people holding companies to account for emissions of other toxins or chemicals that cause damage. So it's interesting to see how increasingly the law is sort of gradually working towards this stage where they're realizing, okay, CO2 is known to be a pollutant that is known to damage the environment and cause damaging impacts on people, and how it's going to resolve this in the future. And so this climate litigation is another area where you could see potentially relevant applications for machine learning. Similarly, social networks and social media, this often entails huge amounts of location-specific data being published, and this could be useful especially in the case where a disaster's going on. You can imagine you have software, it automatically scrapes data from Twitter, it determines where immediate hazards might be by analysing the volume or location of the tweets, or locations that the tweets are talking about, and you can get information to first responders flagging up specific areas of concern, saying, we think there's a fire at the refinery based on XYZ tweets and information, someone should go and check that out. And that might be important to attend to in the midst of a natural disaster. And then again, the same sort of algorithm that can do scheduling and dispatch to determine the importance of sending limited parcels of electricity around on a grid. It's similar structures being thought about that are important for disaster research in the future. Another network that might benefit from machine learning, control and information is transportation. Improved computer vision over time is going to improve the quality and quantity of data surrounding the use of transportation networks, alongside increasing amounts of data within the cars themselves. And we simply know this is going to happen because there's such a push at the moment for autonomous vehicles. If you ever notice when you do a recapture and you have to identify a car or a bridge or a road sign. What you're effectively doing is training machine learning algorithms by labeling datasets for them, and those will probably eventually find their way into the mind of some autonomous vehicle project somewhere down the line. But this does mean that this computer vision is getting quite good at recognizing aspects of transportation networks and mapping out the transportation network as it will have to be. And of course, the more information you have about your transportation network, the more likely you are to be able to allow city planners to design routes that reduce congestion, fuel waste, and so on. Cutting down on unnecessary journeys or alleviating traffic can help to reduce pollution. Uber's algorithms are already very good at matching riders to drivers, and ride-sharing is another alternative means of reducing emissions from transport. And as autonomous vehicles do become increasingly prevalent, although this might take longer than we expect at the moment, they can optimise their routes with emissions in mind and help cut down on this sector. We think so often of climate change as being a problem principally around how we generate our electricity and burning coal in power plants and so on, and how we need to get rid of that, replace them with solar panels and wind. Ultimately, transportation accounts for a quarter of all greenhouse gas emissions in around the world, and there are other sectors such as the heating of buildings and the use of heat for industry that account for a third or more. And it's important to remember that it's not just an electricity generation problem, and that actually some of the sectors that aren't electricity generation can be even harder to influence, because while there are only a few different power plants and so on that you might want to replace, and state and local governments have a lot of influence over that, it's much more difficult to, for example, ensure that every home is properly insulated so that the heating that's being used is being done properly, or replacing every boiler in a country with a gas-fired boiler. Replacing these gas-fired boilers with electrical alternatives or heat pumps is, again, something where there's a lot more actions that need to take place to actually surmount that. So in as much as you think about how it can be used in the sector of electricity generation, there's plenty of other sectors that are really important to bear in mind as well. I mean, in electric vehicles, there's also going to be battery management systems, these things that extend the lives of batteries to reduce the environmental footprint on them and, of course, the cost of the consumer for buying new batteries, that they can increase the efficiency of the battery and the range on a single charge, alongside, of course, smart charging. All of these things are areas where machine learning could have some leverage over time. Now, another thing that's really interesting that's worth talking about is software systems like WattTime. So WattTime was developed with the help of the Rocky Mountain Institute, and what they aim to do is to make information about what the emissions consequences of your actions are a lot more transparent. So they will tell you the marginal emissions reduction of different actions that you can take. So they might, for example, measure the energy usage and the energy supply in your area and tell you, okay, this is how many grams of CO2 you'll avoid by turning off this light at this time, or by doing your washing up at a different moment, or something along these lines. And this is really just making it transparent so that people can actually make better choices. Because it's not entirely clear to me, as an end-use consumer, whether, for example, charging my laptop overnight is worse than charging it during the day, or so on. And this type of software is really important, because it's all very well to talk about people making decisions that are going to reduce carbon emissions and the impact that our personal choices can make, but you don't have any means of measuring the CO2 impacts of what's happening by yourself, and then you have no metric to try and control for, whether you're doing that personally by making decisions in your own life, or whether you're trying to hook everything up to some smart grid that's going to control everything for you. If you don't have these measurements, then you have no prayer of figuring out how to reduce emissions. You can't control what you can't measure. And machine learning is gradually being used to improve the performance of these softwares. So WattTime, as a non-profit organisation, they're hoping to use satellite data and machine learning to determine the actual air pollution and carbon emissions from each power plant in real time, not just by getting these average statistics that are put out by the power plants and trying to map them onto generation or something, but actually genuinely figuring out, okay, how much CO2 is being emitted from this plant right now. And that will circumvent any necessity to rely on dodgy or approximate data from individual plants. Since it can be done by satellites, there's no means of misreporting, and you can actually independently verify where the CO2 emissions are coming from. And it will allow us to understand which interventions, whether it's shutting down a plant or using energy storage at the proper times, are going to have the largest impact on carbon emissions. And that's really important, because one of the things that I think is important to remember about climate change is, if you look at how the economists model this stuff, there are plenty of interventions that should take place at a carbon price of $0. So if you imagine that we're Homo economicus and we automatically are rational actors who can make the best decisions available to us with all the information. There's plenty of things that we would do that would help climate change and reduce emissions that would actually save money, that would save us money, that you would, if you were a fully rational person aiming to maximise your own profit, that you would be doing right now, regardless of whether CO2 did any damage at all to the environment. And I think it's the fact that this information isn't available to people, which is continuing to lead them to make these really, really bad decisions. And of course, in the future, if we ever did get a carbon price where people would be taxed for the things they did that resulted in emitting carbon dioxide, then of course people are going to want to be able to have the information about which of their actions can reduce their emissions as much as possible. They want to know which levers they can pull on to reduce their emissions. And measuring this stuff is so crucial to be sure that you're actually doing that. Because quite often the results can be counterintuitive. I mean, there was an interesting paper a few years ago about the implications of increased energy storage on the grid. So typically we have in our minds this idea that, okay, energy storage is great because it means you can, when you have excess wind or solar generation, you're storing more electricity, and therefore because you have this extra flexibility in the grid, you can use that electricity generated by renewables later on. But it's also the case that if you have energy storage next to a coal-fired power plant, the coal-fired power plant can still make money by burning coal when the demand is low, because it goes into this energy storage and is used later on. So actually, in the early days in California, it was found that integrating energy storage onto the grid actually increased the emissions of the grid overall, because it was more often storing CO2-intensive emissions from coal-fired power plants and making them economical to run than it was storing the emissions from the renewable plants. And so something like this is just an example of where you really need solid evidence-based data and not just expectations to understand which of your actions are going to have the biggest impact on reducing emissions. And of course, for buildings, this is another sector that's huge. Heating and cooling of buildings, alongside some of the more naive stuff, so for example, scanning satellite images for signs of under-insulated properties. This is something that's quite fun to do when you're driving around your neighbourhood, particularly in winter if it's snowed. You can see which places have good insulation and therefore are probably consuming less energy, just by seeing whether there's snow on the roof. If there's snow on the roof, it's good insulation. If it's all melted, then they probably don't have that insulation. So this is even this would be useful to a city planner who is trying to determine which houses to go to and install this new installation stuff, where to apply the subsidies to help people insulate their homes and make them run more energy efficiently. But of course, there's plenty of stuff you can do with machine learning that's even more subtle than that. So for example, you can imagine statistical or machine learning methods that are being developed which are determining which appliances are using the most energy. And this is disaggregation, which is important too, because if your electricity bill or your meter just tells you how many kilowatt hours you've consumed in a month and you don't know which device is consuming the most electricity, again, you're not going to know which levers to pull on to reduce your own personal emissions as much as you can. Now, machine learning can be used to help control the systems for heating and cooling, adapting to differences in occupancy, detecting faults automatically, leading to reductions in energy use. So, for example, there was a case in an Oxford college, I believe, where they had a system that was starting to determine, okay, which rooms are occupied and which rooms aren't occupied when the students go home for the winter break. And if a room is unoccupied, then they stop heating it. Just a simple way, saves money, saves carbon. These are all of the things that would be being done by people in purely to save money, if not anything else, at negative cost to reduce the impacts of climate change, and yet aren't being done at the moment because people either don't know about them or they don't have the ability to control these things automatically. And again, this is the type of thing that you just want to have your algorithm running in the background, churning and working on these things to generate profits for you and generate benefit to the climate for you in the background. So an example of this is it can actually even determine where energy efficiency measures are underperforming the predictions of the engineers who installed them. So for example, Konstantin Contacosta developed a system for predicting the energy use of buildings in New York City, which was later used to grade buildings automatically against efficiency standards. On the research and development side, machine learning is increasingly combined with physics-based models and experimental data to predict how new materials are going to behave. They can do this by encoding the physical properties of how different materials might interact and inferring relevant patterns. Now, this is an active area of research. For example, you can see a recent review by Fujimara et al., which is called Accelerated Materials Design of Lithium Super-Ionic Conductors, based on first principles calculations and machine learning algorithms. And essentially the idea here is, we know that there are all of these different chemistries and different arrangements you can have with lithium. Which of these are we going to predict are going to be the most interesting in terms of their electronic properties for developing new pieces of hardware? People even want to try and use this sort of thing to find high-temperature superconductors, because the high-temperature superconductors, effectively, as we discussed in our episode a long time ago on superconductors, it's all to do with the lattice arrangement of atoms in a grid, and there's many different ways you can imagine arranging these atoms and trying to solve the multi-atom Schrödinger equation and all these sort of things to try and work out what the conductivity of your material will be. If your algorithm can tell you which of these chemistries is most useful, that's going to push you in the right direction when you're trying to figure out what to investigate next. And so some of the applications here, people are hoping we can use this to find materials for flexible, super efficient solar panels or LEDs by predicting which crystal structures will have the best photovoltaic properties, which are the best, most efficient crystals at converting sunlight into electricity. It can be used to design thermoelectric materials, which can turn waste heat back into useful electricity, and it can be used to help find absorbent materials for those negative emissions CO2 scrubbers that we talked about. You could even imagine someday the entire process of choosing, designing, fabricating, and testing a new material could be entirely automated and subject to machine learning control. Although, of course, we're a really, really long way from this happening in reality. But when it comes to something like solar panels, where you can quite quickly fabricate a new piece of chemistry in a particular way and then test it, you could imagine this whole process being done automatically, finding better and better materials that can work under a different ranges of conditions. And, you know, the prospect of this like automated research and development is really cool, I think, even though, of course, it's very likely to be a long way off from where we are at the moment. Now, in cases where we can quickly fabricate new prototypes, like solution processable materials for solar panels, which can be sort of turned into liquids and coated onto platforms and so on, and battery materials as well, these models and machine learning algorithms, what they're doing really is guiding you through this impossibly large search space of different chemistries and designs that you could attempt to build. And every data point that you feed into the algorithm from a prototype that you've actually fabricated, this is going to make it more useful, because you could spend lifetimes looking through all of these different chemistries and materials. You need some sort of guideline about when you're getting warmer and when you're getting towards materials with more interesting or useful properties. And this kind of thing is being rigorously explored, the applications of machine learning at the moment for drug discovery properties as well, you know, trying to determine whether we can find automatically new types of chemistry that are going to have interesting impacts in drugs for treating different medical conditions. One of the other areas that machine learning could be useful for is actually going to be enforcement of the Paris Agreement. So the Paris Agreement is obviously much vaunted at the moment. It's this main international agreement to reduce emissions. All of the countries that have signed up to it have agreed that they are going to try and make efforts to hold global warming to below 2 degrees Celsius. But it's based on voluntary targets and self-reporting of emissions. So there are some problems here, because one, of course, you might define your target in a particular way, and you might define your emissions in a particular way. In fact, there are as many ways of carbon accounting as there are accountants, but there's also the potential for fraud and deception. I mean, probably you're all aware of the news story whereby Volkswagen systematically cheated on the emissions tests for their cars for many, many years. And so, showing up in the data, people would say, well, a Volkswagen car has these emissions, but in actual fact, obviously it was higher. More trust might arise then if emissions could be monitored remotely. And this is really important when it comes to a multilateral organisation like the Paris Agreement Organisation, trying to ensure that we can get around this problem of the tragedy of the commons, which has plagued climate change for so long, whereby people feel that they don't have any incentive to act on climate change unless other countries do the same. I mean, part of this really is just a mistake, because, of course, there are plenty of things you can do to act on climate change that benefit you economically as well. But if you're one of these people who's still stuck in the mud and think that there's some choice to be made between saving the economy and fixing climate change, which there isn't, then you can see why this argument of, oh, well, we shouldn't do anything unless China do it first, still holds water amongst a lot of people. So the idea of Paris really is that everyone can see transparently what everyone else is doing. And you can see that all of your friends, all of your other nations are taking their own actions on climate change. And gradually you'll all sort of motivate each other in a kind of friendly competition to determine which of you is going to cut your emissions more and contribute more to this global pot. And the idea is that in successive rounds of negotiation, people are going to ratchet up their ambition and cut emissions faster and deeper. Now, that hasn't actually happened yet, but one of the key things that would be required for this to work would be people trusting that each other's reports on what their emissions reductions actually are true. So satellite data, including a new fleet of CO2 monitoring satellites due to be launched by the EU in the 2020s, that could allow for these independent measurements of CO2 to take place, which would help nations both take stock of their own individual and collective efforts and identify key areas to work on to reduce their emissions. Now, churning through satellite data, particularly where it requires feature recognition, this is something that machine learning algorithms excel at. They're really, really good at this. Now, there's been a big drive for natural gas production through fracking and other technologies, and this has actually led to increases in methane levels, which are higher than anything we've seen in a really, really long time. Now, there's some debate at the moment in the climate science community about whether this increase in methane is due to a number of different factors. Is it because we have more natural gas pipelines that are leaky? Is it because we have more cows in fields that are emitting methane in their own special way? Or is it to do with feedbacks in the Earth system? There are concerns that there's methane in the Arctic, which as the Arctic melts will be released into the atmosphere. How can you tell, a priori, what the source of this methane is? Well, if you have a satellite that can automatically detect methane, then you can not only locate these leaks and plug them, or figure out which farmer is contributing most with their cows, or work out which parts of the Arctic are melting fastest and producing the most methane and driving up the concentrations of this greenhouse gas. You can start to fix these problems and understand where your emissions are coming from, and that's really going to be the first part of the battle to actually getting rid of them. Now, this isn't all that satellite data can be used for with machine learning. A large part of our uncertainty in how the climate has responded to human influence is due to clouds. Now, clouds are the bane of the climate modeller's life because they can be influenced by all kinds of different things, one of which is pollution in complex ways. Now, machine learning algorithms can scan through satellite cloud data, correlating it with sources of pollution on the ground, and that can help us narrow down this uncertainty and hence better constrain forecasts of global temperature in climate models. So an example is these famous things called ship tracks. If you ever look at a satellite image over the ocean, you'll sometimes see little tracks that look like contrails of planes in the sky. And what's happened here is that the ships on the ground have released pollution, which has sort of formed the seeds for clouds that are then formed later on. Now, it's not well understood by us at the moment, or at least there's a lot more research to do about how this pollution influences these clouds. And the ship trails are a really, really good example because there, theoretically, we know what the pollution is from the ships underneath, so we can work out the trajectories of the ships. And we have some measurements of the atmospheric conditions where this pollution is being done. So it's it's not really a natural experiment, but it's like it's an observation we can make where we know that pollution is happening. And we can try and determine its influence on clouds. And you can imagine a big machine learning algorithm, they already exist, that go through the cloud data and spot these ship tracks and then try and correlate it with where the ships were. And then we can figure out why sometimes clouds are produced by ships and other times they aren't. And that is going to really influence our understanding of this aerosol-cloud interaction, which is a very important part of the fundamental climate science which goes into these models. And I feel like this is probably the area of machine learning which has the most near-term application and maybe the highest likelihood of success, because if there's one thing we know from lots and lots of experience with these algorithms, they're really good at doing these visual analyses of big amounts of satellite imagery. We know that they can do things on X-ray imagery and so on that are analogous to this. And this can have other applications too. You can imagine that it would aid in energy generation indirectly. It could improve forecasts, but it could also do it directly. So, for example, you could use satellite data and automated analysis to find appropriate sites for hydropower plants, geothermal plants maybe, wind plants, solar plants, and they can also, of course, image plants that already exist and to detect the faults in these automatically so that you know when to send out your repair and how to do that. On a more climate and less energy focused side, machine learning enabled analysis of satellite imagery is useful for detecting wildfires and determining how they spread, changes to the landscape that are being caused by climate change, and estimating greenhouse gas emissions due to changes in land use. So actually getting a proper decent estimate of how many trees are being cut down, how many bits of rainforest are being replaced with pasture and so on, which is stuff that's not necessarily that well documented from anything other than through satellite data. And it can tell us the potential decarbonisation benefits of putting forests in places or other large-scale negative emissions techniques that you might do. And naturally, you can also imagine how it might be used for disaster response, and there are researchers working on applications, for example, that might tell you how likely it is that a building has been flooded or will be flooded in a flood, or damaged in a given natural disaster. Now, another area that might be useful is that neural networks are very good at encoding subtle statistical relationships between multiple variables. Now, this means that they can potentially be used to represent physical processes in a more computationally efficient way, allowing us to improve climate and weather models, potentially allowing us to integrate more real-world data and better representations of processes that are important for climate that take place on smaller scales into the models. And this is crucial, of course, because we rely on climate models to understand which impacts are most likely to affect regions in the future, and even to determine whether geoengineering schemes might do more harm than good. So improving these models is always going to mean better decision-making. Meanwhile, those most vulnerable to change live in the poorest nations, where governments are least able to adapt. Extreme heat waves, droughts, floods are often deadly. Machine learning can be used to map informal settlements from satellite data. The first step in disaster response is, of course, knowing where people actually live. And when crisis hits, they can go through the aerial photography, satellite data, and social media posts in real time, providing information to these first responders. And this is important, of course, particularly in places where conventional means of communication are unreliable. Indeed, there are already also startups which aim to use combinations of machine learning, satellite data, and climate modelling to predict how climate change is going to impact the portfolios held by private investors. The idea here is to develop some software that will tell you how exposed you are to climate-related risks, such as extreme weather events, if you own stocks in a company that might be badly hit by climate change in the future, for example. And this is obviously being developed for private investors, but you can see how useful this software would be for governments in disaster planning as well. More speculatively, some fun projects arise from trying to use machine learning to optimize, analyze, and control the output from fusion reactors, including the experimental collaboration between Google and the fusion startup TriAlpha Energy. In the longer run, with tokamaks, which we've discussed obviously at length on this show, there is some application for using machine learning to predict and maybe even try and prevent disruptions, that is, those violent and sudden disturbances in the plasma which prevent the plasma from being contained. And that could even allow for disruption control and mitigation to be done automatically in the future. There are aims to use machine learning to help in the social side of climate change as well. So Yoshua Bengio, who was one of the researchers involved in this project, is aiming to galvanise people into action by visualising possible future impacts of climate change with neural networks that generate imagery of flooded homes. Machine learning can even be used to reduce the carbon footprint of machine learning. The energy consumption from GPUs, these processors that run these algorithms, can be huge, particularly when you're running them to do work that is useless or redundant by design, as in the case of the Bitcoin network, which I've already slagged off in other articles, to be honest with you. Training advanced neural networks comes with a carbon footprint of its own. But of course, saving energy saves money, as well as benefiting the environment. This is why Google seeks to use machine learning to reduce the energy footprint of its data centers by changing operation strategy and cooling techniques over time. And of course, they do save money in the process too. Now, there are of course plenty of concerns with turning over some of these things to machine learning algorithms. Many algorithms are better at interpolating than extrapolating, so when you're moving into unprecedented areas you have no data for, as we will with climate change, you can question the validity of your machine learning algorithms. Those trained on historical datasets can encode historical biases and fail to anticipate how things might change in the future, in a way that a more mechanistic model, one that encodes physical principles into it, might be able to predict the future a bit better, because it doesn't have to rely on always extrapolating from things it's seen before. And this is also very important when it comes to trusting the predictions of these devices. For example, if they can't quickly adapt to new conditions on the grid, they might end up giving people incorrect advice on the best time to use electricity, based on overweighting past trends and not taking into account what's going on at the moment. Now, the open questions, and maybe the huge drawback for this whole field at present, is really one of motivation. The machine learning community has a great deal of specific tools that can be extremely well applied to certain problems. Lots of them have been developed to solve specific problems, like, for example, we talked about the bandit theory and the application of that to determining which ad to send you to make sure you're most likely to click on it. Some of them are well motivated by the desire to find specific applications for what they're developing, while others are just happy to earn insane amounts of money flipping ads to people and driving the engines of surveillance capitalism. The people who hype machine learning, very often not those who are actually involved in coding it, they want to tell you that all of these tools are infinitely generalizable, that they're practically some general AI that can do whatever you want, when they probably aren't in practice. It is certainly not going to be the case that this is a panacea that automatically solves problems, and indeed sometimes it can just be a really complex sledgehammer to crack a relatively straightforward walnut. And everyone who's outside the machine learning field wants to believe that their problem can be solved by rigorous application of some particular machine learning tool which will draw out scientific insights there. So what you need is cross-domain expertise in both the tools and the very specific applications that they're being used for, but that's really hard to build. And so it can end often with machine learning experts occasionally reinventing the wheel for solved or useless applications, or people come over from the climate-specific field and they end up running around trying to teach themselves inappropriate techniques which are ultimately unhelpful. So it's going to be really crucial both to make useful tools of machine learning available to more people, but also to establish a dialogue between the people who have the applications and the people who hope to apply machine learning in order to head off some of the hazards that might arise from this approach. In short, the possibilities for machine learning to help with climate change are all around us. The machine learning revolution is based on the idea that the more data we collect and process, the more statistical relationships we understand, and the better decisions we can make. Climate science is heavily driven by climate data. Adaptation will require policies that are tailored to the individual changes expected in every region. Mitigation will require improvements in efficiency and changes in energy use in virtually every sector in society. And all of these could be better understood and better controlled if we had more data and more understanding. So the time is really ripe, I feel, to deploy some of our most advanced and exciting computational tools to help solve the outstanding challenge of our age. Thanks very much for listening to this episode of Physical Attraction. You can find us on the web at Physics Podcast. You can find us on Twitter at PhysicsPod. You can subscribe to our Patreon at patreon.com/physicalattraction, where you'll only pay when we release a new bonus episode, so it's quite low commitment at the moment, particularly when I don't get round to releasing the bonus episodes. If you enjoyed the show, there are plenty of things you can do to support us. One of the main ones would be to tell as many of your friends about it as possible. You can also go via the website physicspodcast.com and contact us via the contact form there with any comments, questions or concerns you might have about the show. It's always great to hear anything that people have to say in response to the stuff that I've done. Until next time then,